All right, my name is Tyler Jordan, and I am a CBT undergraduate fellow here at the University of Michigan. And some of my work with the CBT has been investigating the temperature dependence of organic scintillator response, which is what I'll be presenting to you today. However, before I jump in, I would like to motivate this investigation. So clearly, versatility and robustness in radiation detection is a priority across the field of nuclear engineering. And an important aspect of ensuring that detector systems function as they should is investigating the systematic uncertainties introduced by external influencing factors such as temperature on detector systems. Anytime a detector system is in an environment where the temperature is not controlled, it's going to encounter temperature gradients, and it's important to understand how these changes in temperature affect detector performance. For this talk, I'm focusing on organic scintillator detectors, which have three main components: the organic scintillator itself, some sort of photosensor, and a voltage divider. One benefit offered by scintillator detectors is pulse shape discrimination, where we can distinguish between gamma counts and neutron counts by analyzing the shape of pulses collected by the detector. Another important point for the rest of the talk is that each component of an organic scintillator has a distinct dependence on temperature, and this analysis considers the dependence of the system as a whole. So the two main objectives for the experiments that we ran were to characterize the calibration stability and the pulse shape discrimination stability of a liquid scintillator with changes in temperature. We selected target temperatures at room temperature, 30 degrees Celsius and 40 degrees Celsius, and we planned radiation source measurements at each of these temperatures, where we would then investigate the pulse integral distribution, the energy resolution, and the pulse shape discrimination at each of these temperatures. The detector that we used was an EJ309 liquid scintillator with a cylindrical active volume that was 3 inches tall by 3 inches in diameter, and it also had a Vortec embedded PMT. We used a Kane DT5720 digitizer with 4 analog input channels, a 2-volt dynamic range, and 4 nanosecond time resolution, as well as a Kane high voltage power supply with selectable polarity. We monitored the temperature during the experiments with an X-Tech SD700 data logger, and the experiments were carried out in a thermal chamber located in the Neutron Science Lab here at the University of Michigan, and the thermal chamber is controlled by a ULABO FL601 recirculating cooler, and both the chamber and the cooler are pictured here. As you can see, Wolverine pride penetrates even to our thermal chambers. If you, opening up the chamber, you can see the experimental setup inside. Towards the top of the chamber, we have fans and pipes which ultimately connect to the recirculating cooler and allow for a temperature ceiling to be set inside the chamber. And at the bottom of the chamber, we had a hot plate that was we used as a heat source to raise the temperature in the chamber. In the middle, we have our actual measurement setup, which consists of our temperature data logger, the scintillating detector, and a clamp to hold the source. For the calibration stability study, we used a cesium-137, which is a source that emits gamma rays of a single energy. And another benefit of cesium-137 is there's a feature in the pulse integral distribution, known as the Compton edge, that provides a constant point of reference for calibration. While the target temperatures for these measurements were room temperature 30 degrees and 40 degrees, our system ultimately reached steady state temperatures at 26, 39, and 30 degrees Celsius, as can be seen in the temperature plot at the top right of the screen. So we define the Compton edge into pulse integral distributions as 80% of the maximum value of the falling edge of the Compton continuum. And we computed the energy resolution by computing the full width at half max of a Gaussian fit to the falling edge of the Compton continuum. In the bottom right of the screen, there's a plot that shows the pulse integral distributions for the 30-degree test and the 39-degree test. We experienced some unexpected fluctuations in the voltage settings during the 26-degree experiment, and we will have to repeat that experiment to get meaningful data. However, what we can see is that as temperature increases, the Compton edge shifts towards lower pulse integral values, which corresponds to a decrease in detector gain. For the PSD Stability Approach, PSD Stability tests, we used Californium 252, which as a spontaneous fission source emits both photons and neutrons. Here the steady state temperatures were at 27 degrees, 31 degrees, and 39 degrees. So in the bottom right of the screen there's an example PSD plot. Once again, we can analyze the shape of pulses to distinguish between neutron-induced pulses, which correspond to the upper point cloud, and gamma-ray-induced pulses, which correspond to the lower point cloud on the plot. So we optimize the parameters that we use to analyze these pulse shapes, and then we fit a quadratic as the gamma-neutron discrimination line. So I actually have, we analyze the pulse shape collected at each of these temperatures. Now, to compensate for this shift in the PSD clouds, there's a corresponding shift in the gamma-neutron discrimination line. This allows us to actually quantify the effects of temperature on PSD by applying the 27-degree gamma-neutron discrimination line to all temperature cases and observing the trend in the ratio between gamma counts and neutron counts. And as we see, using the 27-degree gamma-neutron discrimination line, the gamma to neutron ratio increases with temperature, which is according to our expectation because the discrimination line remains constant while the point clouds move down, which means that neutron counts are beginning to be classified as gamma counts. So to summarize the results, we found that with increasing temperature, the Compton edge shifts towards lower pulse integral values, which corresponds to a decreasing gain in the detector. And we also found that the PSD point clouds shift towards lower tail integral values. For future work, we plan on, as I said before, rerunning the room temperature experiment for cesium-137 in order to gather data for that case. We also would like to test the PMT with an LED driver to begin decoupling the temperature dependence of the different components of our system. And finally, we hope to perform experiments over a constantly changing temperature to see what sorts of trends we observe there. And so with that being said, I would like to open it up for questions.
So we imaged all of these sources with bare or no shielding, and then we also imaged them with polyethylene, iron, and tungsten to cover the